Lots of homework, lots of studying, projects are ramping up. Not yet? Maybe not yet. That's like 3 weeks away. We'll start up in 15 seconds.
Oh, we're already running.
Okay.
I'm ahead game today. You're gonna have to put all that out, but.
All right, let's get started. So, last time we were talking about some variance estimation, and I'll just tell you how to work through these problems. We'll see a couple interesting things come through. I'm going to simplify everything, and I'm just going to talk about a one data point example. And so we could have done that for our old analysis too. Instead, we used X bar and everything. Let me just ask you a question. If I did have multiple data points before we even begin, what's my sufficient statistic? I could write down the likelihood in a number of ways. If I didn't know the answer to that, I could just product through. Product together all the conditional distributions, and then conceptualize them as a function of your parameter space. Plug in all your data points, one for each term in the product, and that will be your likelihood. If I didn't want to do that, could I do something else? I don't like the idea of going to my computer and typing in this big product. So I am a couple steps ahead, and I'm always thinking about what am I going to do with this thing and computability. So just a simple question. What is the sufficient statistic for sigma squared? Any one-to-one transformation of a sufficient statistic is sufficient. So if I'm doing things on phi and it's just the inverse, then it will just be the inverse of your sufficient statistic. What is it?
The sums of squares centered.
Sums of squares, right? So there's a little bit more to it. How do I write it down?
The sum of xi minus x bar squared.
Sum of the xi's minus x bar squared. So here's one answer. So let's just write down the question. What is sufficient for sigma squared? And I'll say or phi. This is a one-to-one transformation. It's not a unique answer to these questions. One-to-one transformations of sufficient statistics are still sufficient if the information is there and I can always go and get it. No matter how you've transformed it, as long as I can go back and I still have the info. So Annie said this. Sum of the xi's minus x bar squared. Some people might know what to do with this thing. Some people will divide it by n and get you an estimator for sigma squared. Some people will divide by n minus 1. Again, those are one-to-one functions of my sufficient statistic. I'll let you ponder if you like to divide by n or n minus 1. Anybody that's taken my class knows which one I'll divide by. Which one?
N.
I like n. Don't like n minus 1. We can talk about that later. I don't put a premium on being unbiased. I put a premium on being closer to the true answer. And so it turns out that one is usually closer to the truth. Talk about it later. It has to do with the variance of your estimator. And so, but I will remind you, I'm also going to give you mu in this. So our example is mu is known. And so let's start with the conditional estimator. So if I gave you mu, you might change the answer to this just slightly. So this is if I didn't give you mu. But if I give you mu, you might want to use that. What's x bar estimating? It's estimating mu. Now, if I gave you mu, we wouldn't have any debate over to divide by n or n minus 1. We would just divide by n. We would pick up a degree of freedom in there. People that have been well-versed in inference understand this stuff. Might be a little technically nuanced, but I'll just write this down. If I give mu, we might probably use sum of squared differences from mu. Similar answers. And if n was big, you wouldn't be able to tell the difference. Okay, so keep in mind, if I'm answering one of these questions, I don't get to plug in x bar for my sufficient statistic. This characterization of the data is totally different from x bar. I've seen people go and say, I'm going to do Scotland's trick, and I'm going to write down the likelihood and just use x bar. And they make a big error when they do that, because that's not sufficient for sigma squared. You've left out some of the information. So we'll talk about all those issues soon. But we'll just go with the one data point thing, and then it's kind of a moot point. I've got one data point, there's nothing else I'm going to do with it. So to use that data point, try to infer the precision, or sigma squared, if you will. Now I did write down real quickly what the various forms of likelihoods look like. So these would be the likelihoods that I would use. If I were using phi, I'd write down this likelihood. It looks just like this thing if I were using sigma squared. I'd use that likelihood. I don't need the 1 over root 2 pi, so I'm going to get used to not writing it down. But that's just a normal distribution. I just plug the data into the function it came from. Now I've plugged in a number that I have from sampling. I plug it into that, and now I have a function over sigma squared. Or if I want to reparameterize, I have a function over phi. And so, depending on what I write down here, it changes the answer to my next question. So to conclude the Bayesian analysis, I need to multiply one of these two things, depending on which scale I want to do inference, sigma squared or phi. I need to multiply by a prior. And so my question, I think right near the end of last time, I had asked, what's the conjugate prior? And these are certainly questions I'll ask on exams. You'll be working in standard exponential family stuff. And in those cases, conjugate priors exist. It's not always the case that you have a conjugate prior, especially in joint models. You know, if I just asked, what's the conjugate prior? If I didn't know both mu and phi, what would it be? I have no idea, but I can discuss a conjugate prior for each one holding the other one constant. And so conjugacy doesn't always exist. It's a convenient thing, and if you were operating in the 1960s, it might be your only tool. Good news is there's lots of good theoretical properties that we get out of the old stuff too. So we can still use limiting forms. But what's the conjugate prior? It depends on the form of the likelihood. I'm going to multiply it by through, so it's going to change the answer if I reparameterize it. And so what's the conjugate prior for the precision parameter? For phi, this is precision. If my variances are big, I'm not very precise. If I'm very precise, my variances are small. That's the inverse relationship. What's the answer to this? Did we say last time? Yeah, it is. And we can kind of see it. We look at this thing, and if we're familiar with distributions, we kind of go, well, it does look like a gamma and phi. I wonder what happens if I multiply by gamma, and it preserves all that form. And so the answer is gamma. And gammas have two parameters, usually denoted by alpha and beta. And these would be hyperparameters. They're knobs that I get to turn and change the analysis. And so I better have good reason for picking some of them. And I'll give you some default choices today. If you had information about what you thought phi was, its expectation and its variance, maybe you could tune those to try to lock that in. It'd be a subjective Bayesian analysis. You don't get to use that data in the likelihood. If you do that, that's a gross violation. Talk about those repercussions. And so what does this look like? Pi phi, given alpha and beta are hyperparameters. This is what a gamma looks like. I write it down like this. There are other formulations of this. So this is going to be phi to the alpha minus 1, e to the minus e beta. So that's what it looks like. You'll notice that in some textbooks, instead of multiplying by beta here, they'll multiply by 1 over beta. It's the difference between a scale and a rate parameter, and they're arbitrary conventions. I can parameterize them either way. Doesn't change any of my answers, but I better be consistent. So if I run over to MATLAB and I try to use this, MATLAB will give me the wrong answer than what I'm anticipating, because MATLAB encodes their gamma distribution differently. They'll divide by the betas. In an R, you can say whether or not you have a rate or a scale, so be very careful of that. I've seen this at least a dozen times over the 13 years that I've taught this, and people come in and they're like, I'm so frustrated with this, I've looked through every line, everything looks just like what you did in class, and I keep getting this nonsensical answer, and I'm like, oh, you need to specify that that is either the scale or the rate, the opposite thing of what you did. They change that one thing, and they're like, I just lost 15 hours of my life looking for this. So, it does happen. It's happened to me. It still happens periodically, but now what I do, anytime I use a default function, some built-in function, I type in help, and I look at what it is first, so I don't assume I know.
It's the same for the exponential and the lambda. Sometimes it's very...
Yep, absolutely. Exponentials are like that as well, and you'll notice this kind of looks a lot like an exponential. And so it turns out when these numbers are something, I can default to an exponential. So when that thing right there is 1, right there, alpha is 1, this is an exponential. So naturally, exponentials have this as well. Lots of distributions are like that. Okay, so somebody help me out just real quickly. What's the expectation a priori? It's just a statement about gammas.
Alpha over beta.
It's alpha over beta in this form. And if you were working through Casella and Berger's textbook and you looked in their index on distributions, they would have alpha times beta because that beta would be flipped upside down. They treat it differently. So they divide everything by beta in here, and so it changes its answer. And everything just flows through real nicely. What's the variance?
Alpha over beta squared.
You got it. If you know the variance for a beta distribution, you would know for gamma. So that's where people usually break, but there's no fooling Annie. She knows all these things about these distributions. Okay, if I changed the question and if I asked what's the conjugate prior for sigma squared, what would the answer be?
Inverse gamma.
It's inverse gamma. That's just a different distribution. It is the same distribution that if I took elements from a gamma and I sampled from the gamma and I inverted them, I would get an inverse gamma. It would be distributed differently. And so the distribution for the inverse parameter would just be the inverse distribution for whatever this was. I don't like to work in inverse gammas simply because I already know everything I need to know about gamma distributions. And so since they're the same in some sense, they are different, but I can go from one to the other. And a one-to-one transformation, they contain the same information. So I make a choice that I'm going to work with gammas. Why did I make that choice? Well, my teacher used it. All my teachers used it. Everybody in America uses this. But I will tell you, if you end up going to a different country, they might be using inverse gammas. Or inverse chi-squareds in England, they like to talk about a lot. And I just like to mitigate that and always do this on a gamma scale. Arbitrary choice keeps my life easier. So let's finish up this problem because we almost have the answer to the conditional problem when we know mu. So I'll remind us we know mu. When we know mu, our posterior, and this is going to be under the conjugate analysis, would be this. Pi phi given x, and I'll remind us that we know mu in my notation. And you'll know from the right-hand side of this equation that I must have a mu to plug in because it's going to show up in the equation. But it's just going to look like this. beta alpha, gamma alpha. I'll multiply my prior in first. Phi to the alpha minus 1, e to the minus beta phi. And then I'm going to multiply by my likelihood. That's going to look like phi to the 1/2, e to the minus phi. I'll write this just a little bit differently. X minus mu squared divided by 2. And this thing can be simplified. So this is going to be beta alpha over gamma alpha. Keep in mind, these are numbers. If you're going to actually roll the analysis, you've picked beta and alpha. And so these are just numbers, and since I've written down up to proportionality right here, I can stop worrying about that stuff. It's not helping me. I haven't normalized this equation yet. That's going to be part of the normalizer. And so I'm just going to get rid of that part and just look at phi. And this is going to be alpha plus 1/2 minus 1. So I just add together those two exponents. Same thing happens with the exponential term. So I get two terms in here that add. Beta plus x minus mu squared over 2. And I would recognize this as a gamma distribution. So this thing right here is a gamma. This is going to have parameters alpha plus 1/2. That's this. Right here, keep in mind the gamma always has this minus 1 term. So I never absorb that minus 1 in any of my calculations. I don't try to wrap it up into that half term because I'm going to end up untangling it anyway. So that minus 1 is always sitting there, just like beta distributions, you've got the minus 1 terms on the exponents. So I always just leave it alone. I'm going to use that thing. And then I end up having this term right here, beta plus x minus mu squared over 2. Let's find the expectation of this thing. So expectations, at least, I don't consider them like real answers, like here's your expectation, I'm done with the thing. But when I'm trying to inspect things, I do look at what expectations are because they're on scales that I normally understand. And it's like, is that even in line with what I expect it to be? Variances, not so much. I don't have good intuition, so I usually look at the first moment and try to decide, does it make sense? So let's do the same thing, and we'll do this throughout the whole class. Does the answer make sense? So the posterior expectation, phi, given x, and I'll remind us that we know mu in all of it. This is going to be alpha plus 1/2 over beta plus x minus mu squared over 2. And so this is our posterior expectation. And of course, I could swing this all over the place if I made alpha some like very large number. So push this thing all over the place. I can make it real small by making beta really big. So I've got a lot of control through these hyperparameters. So here's a question for you. What would you pick? For alpha and beta?
I'm just going to randomly say a half and a half.
A half and a half. Okay, so the beta thing, maybe there's some magic there. A half and a half. And remember when we picked a half and a half, we got answers that kind of made some sense too. But it did do some weird penalization, so that's one answer.
You do want alpha over beta to be mu, right?
I'm inferring phi. So mu is given to you.
Right, so wouldn't you want to choose alpha and beta so that their ratio is equal to mu?
Why? I'm estimating phi. Mu
I
is
don't
just
know,
a
I
number
guess,
that I'm giving to you to center everything, so I'm not estimating mu. Remember what the prior distribution is on. It's on phi and it doesn't have anything to do with mu.
Okay.
So probably not, but maybe there's some genius going on.
No, I see. It's expectation of, yeah, it's nothing to do with mu, yeah.
It doesn't, not the way we frame
Right.
it. So how about this other answer that we kind of liked? Remember what we ended up saying, how would you estimate sigma squared if you were to do this? So going back to that, so how would you have estimated sigma squared, and we came up with, we might use something like this. I'd look at sum, I goes from 1 to 1, we only have one data point. X, I, we've only got one x right here, minus mu squared. And if I were dividing by n, I would divide by 1 in this. So this is just x minus mu squared. That's what you probably would have used as your estimator. If somebody just walked in and said, I've got one data point from a normal distribution, here's mu, what's your best guess at sigma squared? I'd have no problem just like, it's not a real question. I'd kind of laugh and I'd use that. So if you're going to be so cavalier about this whole thing, I'll just give you a very cavalier answer. But that answer has some decent properties. Probably a lot of variance in that thing because n's not very high. But that would be maybe our sensible answer. Unbiased answer. Does a lot of good things, and it's min variance. So lots of good reasons to choose that. If you want to know more about that, take an inference class. So what might I pick for alpha and beta to try to at least get back to an answer that has good properties?
0.
0, 0. So that's actually a pretty good default. And I know that what I've done to get Daniel to say 0, 0 is I asked you to appeal to your classical rationale. That might feel very backwards for you. Like, why am I setting up Bayesian analyses to yield classical answers? Like, somehow we think this is a good answer. And I agree that's probably a pretty good answer. But there's going to be other reasons I give you. Things that you can derive so you get 0 and 0. It turns out that alpha equals to beta equals to 0 yields. I'll say a lot of good things about this. Turns out it's going to be Jeffreys. I haven't said what that means. Does anybody know? Anybody had like a undergrad Bayes class? So Jeffreys priors are special priors that if I use the rule that Jeffreys gave us, we'll talk about this rule soon, that I have transformation invariant answers. That if you use the rule that Jeffreys gives you, and I use the same rule that Jeffreys gave us all, and you transformed on any scale, and I ended up transforming on a different scale, then I could come up with a prior. We'd have different priors. But once I came up with a posterior and I transformed my posterior, I would get yours. So we'd be transformation invariance. So imagine Ryan says he likes using transformation scale 1 and I like using transformation scale 2. Jeffrey's prior will give you a prior so that when he does his analysis and I do mine and I come up with Jeffrey's prior, it'll be a different prior because I'm working under a different parameterization, but the information will be in some sense equivalent. If I transform my posterior, I will get Ryan's posterior. So that's transformation invariance. We'll have whole lectures on that. But it turns out the 0, 0 case is Jeffreys. It has that property. That's kind of cool. It's also reference. That's another word. We'll learn this towards the end of class. But in some sense, it means that it has minimal information. So that the posterior converges to the right thing as fast as possible.
So here the 0, 0 is Jeffrey's prior rather than the half-half?
Yeah, it turns out.
Oh.
So the half-half is for the beta, and 0, 0 is for the gamma.
Is this an improper prior?
It is, yeah, so let's keep talking about it. There's lots of cool stuff to check out about this. So that might make you uneasy. But keep in mind there's a big difference between the beta analysis that we did and the gamma, that the gamma lives in this non-compact space. It's unbounded. And so you might think to have these things where it converges just as fast as it can in some sense. I have to give you a distance metric to say what I mean, but it's pulling away from the prior as fast as possible. And the distance metric for doing that is the Kullback-Leibler distance. And the things that you get as a result of that, things that optimize that are the reference priors. It's an exercise in variational calculus to do all of this. We'll have a lecture towards the end of class, but it's going to be improper because you don't want to put too much mass in one part of the space. You want everything to pull away from that as fast as possible if you put the mass down wrong. And so it does turn out that all of these priors that we get with these optimality properties will be improper. tell you what that means in a second and what the repercussions are. But if I pick 0, 0, we get kind of the classical answer. I end up getting, in this case, is 1 over that answer. The halves cancel out, and that kind of makes sense because I'm doing things on the reciprocal scale. It's also hard invariant. To scales. This is scale parameter, so it should be that. I'll give you a full lecture on what that means, but 0, 0 does more than just match our classical rationale, and that's why I'm telling you this stuff right now. So I don't have time to tell you everything about that, and what a cool analysis we just got, but we got something that at least makes sense to us. Okay, so that's an easy analysis to do. Piece of cake. And if I gave you n data points, you could carry this through. I'm going to ask you to do that on your homework. Christina?
So maybe I'm just missing something, but whenever we wrote the likelihood, we mentioned that you would be more likely to use the sufficient statistic, whether it's summation of xi minus mu if we know mu, or summation of xi minus x bar if we don't have information about mu. But in here, we didn't do the product, nor we...
I didn't need to because I have one data point.
Oh.
So I made it really simple, so I didn't even give you those choices to make. We will do the multi-data point analysis soon.
Oh, and that goes, because also for sigma squared, I would say it should be divided by n because you don't like the n minus 1.
So I divided by 1,
Yeah.
and I just didn't write it down because I'm a conservationist.
Oh.
So,
Yeah,
but
just-
you got it.
Yeah.
You got it. Yeah, we're on the same page. It's just that I used one data point. Let's do another analysis. This seems a little contrived, but it at least shows us the steps. So let's do a slightly different analysis. Let's learn example. I'll write x comes from a normal distribution with mean mu, variance sigma squared, which is 1 over phi. Okay, so I'll write it down with 1 over phi.
Isn't it gamma 0, 0 flats?
Yeah. Okay, so this probably, let's back up. So we'll come back to this in a moment. Yvonne wants to know about this. Ben brought it up too. So remember, a gamma 0, 0. It looks like this. So it's going to be 0 to the 0, gamma 0. We'll write it all down. Phi to the 0 minus 1, e to the minus 0 beta. What's this stuff?
0 and 1. Sorry.
It's 1. So you'll have to do your limits and convince yourself. It might be all messed up too. It might not be well defined because this thing is improper. So let's not worry about the normalizing constant because this thing is going to give you a headache. But here's the kernel of the distribution. So what is this thing 1 over phi? It turns out this thing doesn't mean what you think it means at all once we do this. Improper distributions are weird. These parameters are supposed to be positive right here for a proper distribution. But at the end of the day, I wind up with this thing. So gamma 0, 0 is proportional to this. It's not equal because the normalizing constant is all messed up. So I'm going to write proportional to it. If you tried to integrate between 0 and infinity d phi, we've all taken calculus, and we know there's no equality right here. So this is a log of things, and as I push it out to infinity, it blows up. So this thing I'll write rather cavalierly is equal to infinity, but I should limit out as I push that. This goes to infinity.
Even where she had one direction going to.
Negative, yeah. So this thing is bad. It's improper. It's not normalizable. And so, now that might bother you a lot. That it's like I'm doing Bayes' theorem, but I'm using improper priors. But again, we're not doing inference off of the prior. We're using the prior as a mechanism to regularize the space. So this is penalizing the space, and it's saying smaller answers are kind of better, but I don't want to push towards smaller answers too fast. If I started powering that thing up, it would start squashing everything towards the corner. And so This has a ton of mass out in the tails. How much mass is this thing cutting way down on very large numbers? An infinite amount of mass. So even though you think this thing is squashed towards zero, there's more mass in the tail, even though it's getting really skinny. So I would agree that when I first saw this improper stuff, I thought, this is really weird. What does this do? What does it mean? And I got comfort by looking at what the properties of the analyses were. So to me, it's not exactly a probability rule because I'm using it on non-probabilistic forms of things, but I'm guided by probability rules. So let's look into this example and see if this thing hurts us at all, doing this improper thing. Let's try to build this analysis up. But right now, I just want you to at least have an open mind and think that these improper priors seem to be a pretty good idea. If you wanted to, and you were super bothered by this being improper, why don't you just truncate it at like 10 billion? Or whatever your favorite big number is. You know, trillions. And you would have the exact same, almost the exact same practical application of it. But it'd be a little bit different. So think about that for now. What somebody that does functional analysis or was acting as a real mathematician would end up taking a limiting sequence of the alphas and betas and drive them towards zero. So they would have a proper posterior all the way until you get into the limit. And so they would be using this sort of asymptotic argument. And they would say everything's okay.
I think one interesting point, though, is even the scaling constant will change based on exactly how you do the work.
How do you do what?
How you do the work.
Sorry, I couldn't hear. Oh, how you do the limit.
Yeah.
Yeah, there are cases like that. So I'm talking about the linear limit. But you're right, there are all these considerations. What if I take the limit in lots of different ways?
Yeah.
And could I make the limit act real weird and get a different answer? The answer to that is yes. So how you take the limit does matter. That's true in a lot of problems. Lots of weird stuff happens if you take the limit differently. But I'm going to do just the linear sequence. Okay. So let's go to this example and just try to butter it up a little bit more. Maybe we'll like the answer, maybe we'll be equally bothered, maybe we'll be even more bothered by what we do. So I'm going to say x comes from a normal distribution with mean mu and precision phi, which is 1 over sigma squared. So I wrote it a little bit differently that time. This is just one data point. For working through some of these mechanics, this can be a useful tool. And I want to learn phi, but we don't get to know mu. So both things are unknown to us. I want to infer one of them and somehow get rid of the other one. Now you might say just plug in x bar or something and I'll ask you, what did you just do? Do you know the repercussions to doing this? You might say no, and then you work through it and decide whether or not that's a good thing to do. What you really want to do is a Bayesian is you want to average over what you think mu is. You want to marginalize it out of the equations. So to go from pi mu, so what I might do is I might try to infer both parameters jointly, mu and phi simultaneously, to pi phi given x, the unconditional analysis, we just need to integrate. And you can call this operator whatever you want. Sometimes I call this marginalizing or averaging. If we did construct a probability distribution, if I average over one thing, its probability mass just sums up to 1. So everything is just acting is a continuous averager. And so pi phi given x is just going to be equal to the integral. I really like Bayes because I can just kind of follow my old rules. You're working in a probability space, so you just always adhere to probability rules. Never break them. So that's all we would do to do the unconditional analysis. Come up with the joint, and then average out the thing. Let's see if we can do this. Shouldn't be too hard. So real quickly, before we begin, proceeding, we need priors. Mu and phi. What would you choose?
So for mu, we said previously the conjugate prior would be also a normal.
Would be a normal, and then I gave you an analysis, and we followed that through, and we limited that thing, and we came up with an answer we wanted. And so we'll ask you in this thing, be specific and knock down your hyperparameters. So how would you hyperparameterize it? I want a real answer this time. I want something I could give to somebody and say, I plugged in numbers for my hyperparameters. So Christina says, correct answer is conjugate because I can do it. I'm going to ask her just a little bit more. State your conjugate prior. I'm not going to tell you anything more about the nature of the problem other than what we just wrote down. Pretty sure I gave you a pretty good default normal. David, you're a smart game. You know the answer to this, right? I'm leading you guys at least. Maybe they're good answers, maybe they're not good answers. Don, what do you think? What's that?
No idea.
No idea. Okay, let's just go back. So let's do the last two lectures again and say I want to infer mu. And I want a good answer on mu, and I'm going to give you sigma squared. Flat prior. Thank you, Melissa. So how about a flat prior? It's at least a choice. It's, you know, no idea. Melissa has an idea, and she could even give you the reasons for her idea. Give me one reason you like flat.
Everything is very equal.
Yeah, so shift parameter, so I want this R invariance. I'm just going to make it sound like it's more technical. So, seems to be a good thing. So maybe this. And I'll put in maybe. But I want real numbers. I want to actually, like, imagine I've got an X and do a real analysis. I can't just hand to somebody, here's an equation with some knobs, you go ahead and turn them. I have to give them reasons for why I've turned them in the direction I did.
So it's a normal limited to a sigma squared goes to infinity, right?
Yes, ma'am. So, easy answer. That's at least one such answer. What would you pick here?
So
We could redo this whole lecture too. We just got done.
1 over 5.
Maybe that, yeah, exactly. 1 over p. So maybe. So again, these are both maybes, but we saw good default behavior out of them in our analysis.
I also say in this case, I mean, technically speaking, gamma 0, 0 instead of 1 over p, because that would be something improper and,
That's why I wrote proportional too.
oh,
So, yeah, I think writing equal would be a bit of a misnomer. But as soon as I write proportional to, I think I've at least stated what you're stating. And we've done it on both of them. So yeah, a couple different ways we could state this. So these at least seem to be good. Seemed pretty good. At least marginally. I'll say at least conditionally. And if you wrote this down and you used the product of these two priors to be the prior on your joint space, you'd say a priori. I just am not injecting information or relationship between mu and phi. Don't know. If I had told you what mu was, I don't think I'm telling you what phi is. I don't have a mechanism for doing that. And so these would be jointly independent. Let me just ask a quick question. Are phi and mu independent in the posterior? They're not. How do you recognize that, David?
Factorization.
Factorization. Can't be done. We'll look at that in a second if that went over your head. So, pi, here's our analysis. Mu phi given x is going to be proportional to the likelihood function So I'll write it down like this, phi to the minus phi to the half, e to the minus phi x minus mu squared over 2. And then I'm going to multiply by my prior, times 1 times 1 over phi. So that's prior. So I'll write this down as pi, mu, and phi, and they're factorizable. So it tells me they're independent. If you end up looking at phi and mu, you will never be able to untangle those from each other in that equation. They're always going to be stuck together. You can't factorize them. So they're not a posteriori independent, but a priori, the information that we supplied was independent. There may or may not be better ways to do that. Most people will take the product of reference priors. And so usually do a sensitivity analysis on did it matter that I didn't model the relationship. Hopefully your data is guiding all that information. And so this thing just looks like this. Phi to the 1/2 minus 1, e to the minus phi x minus mu squared over 2. Now we have a couple choices. I haven't been explicit. I've been talking about learning the variance, but we could easily learn the mu from this as well. And so we've got a joint model. So joint model. And we could use it to learn kind of 3 choices right here. Mu, after integrating out phi, or I could learn phi by integrating out mu. Or I could learn the joint relationship, and that's exhibited in this function. Later in class, I'm going to show you what this looks like jointly. Okay, it probably looks a little bit different than you think, but it will show the relationship between phi and all of the data. What I'd like to do later in class is also pump up the sample size so you can see how the sample size affects their relationships. So, or I can learn jointly. Mu and phi.
But given that they're dependent on each other, the joint would not be the product of the modulus.
It's not. That's what we're saying is that it's not going to be because you can't untangle these two things. You will not be able to factorize phi away from mu. Okay, so let's choose one of those. Let's do this one. Let's learn about mu because we understand mu better. We can go back and do the other analysis. I've asked you to do it on your homework, in fact. Okay. Let's learn mu. We could easily do the same thing for phi, but let's learn mu because it maybe means more to us. Mu. So what we're going to do is we're going to integrate this thing. Now keep in mind, this is all up to proportionality. I haven't normalized anything yet. So this is going to be pi mu given x, unconditional on phi. So I'm integrating it out. So this is just going to look like phi to the 1/2 minus 1 e to the minus phi x minus mu squared over 2 d mu. So I need to do this integral. Where does mu
over
live?
phi, right?
What's that? Oh, d phi. Yes, sorry. I give myself choices and I can't decide which one. Yeah, that's the one. So this goes between 0 and infinity. Mu is going to live between minus infinity and infinity. So we just need to know how to integrate this. Is that hard?
You should plug it into Mathematica.
Yeah, you plug it into Maple or Mathematica or whatever your symbolic language is, and it would do it for you. Who said that? Yeah, the mathematician in the room gave us permission to, that's what I would do too. I can't remember how to do all these integrals. How would you do this if you were in calc class?
Gamma kernel.
Say again, sorry, my hearing.
It's a gamma kernel.
You would what?
It's a gamma kernel, so you can.
How would you have
solve-
done it in calculus class?
Oh, integration by parts.
Parts, yeah, you'd probably do it by parts. If these numbers were big, then you would do sequential parts. Keep doing it until you recognize the formula, and by induction you have something. And Annie said, forget about all that. I recognize this thing. This looks like the kernel of a gamma. So I know what gammas integrate to. If they were normalized, they would integrate to 1. So this looks like a kernel of a gamma. Which gamma is it? Well, I can look at it right here. It's half. And I can look at this parameter right here. X minus mu squared over 2. So that's which gamma it is. If this had the proper normalizing constant, beta over alpha, I'll call this beta tilde for a second, and alpha tilde. Then I could recognize the normalizing constant. This thing will be proportional to the inverse of the normalizing constant. So inverse normalizer. Since I know what a gamma looks like and I know what its normalizing constant looks like, it's going to be the inverse of it. And so this is going to be gamma to the alpha tilde over beta tilde to the alpha tilde. That's the normalizing constant flipped upside down for a gamma distribution. So again, gammas look like this. Beta to the alpha, gamma alpha, z to the alpha minus 1, e to the minus beta z, if z were the random variable. So I know that it's a probability distribution and it integrates to 1 so long as I have it all worked out correctly, but I think I do. And so I know this integral will just integrate to the inverse of the normalizing constant. This thing right here is just a number. That's a number. We could figure out what it is by plugging in a half to it. And you might know what that number is, and cool if you did. It doesn't really help us because this thing was always up into proportionality in the first place. And so this is going to be proportional to 1 over beta alpha tilde. And I'll just plug in those numbers right now. So here's our solution that we get. It's going to be 1 over x minus mu squared over 2 raised to the 1/2 power. And that thing right there is proportional to 1 over absolute x minus mu. So that's my posterior. I should just flip it around, if you will, if you'd like. You could write it like that, too. This is the random variable. And here's my data point. What do you think of that answer? Some distribution. Can you recognize it? So again, x is an element of the reals, some real number, and mu is an element of the reals. They both live between negative infinity and infinity. How do you like this answer?
It looks improper.
It's improper. And so Ben noticed this the first time, no surprise, he's picking up on it the second time. This posterior itself is improper. It's a horrible answer. Horrible. Answer. Since it's improper. So I didn't have a problem with improper priors, but I've got a serious problem with an improper posterior because I want to make a probabilistic inference. I was trying to use Bayes' theorem so I could put everything on a probability scale, but if I can't normalize it, it doesn't live on a probability scale. This is not a probability distribution. So what do you think we should do?
Change your prior?
Change your prior. So throw some mass in there. So think about what we've done. I've asked for two things. I've asked for both the centering of the distribution and the spread. and I've given you one data point to do it. There's not information about both of those things in the one data point. My priors were improper, so they're not giving enough traction for where the answer could be. And so it does kind of make sense if I went to your classical class and I said, here's one data point, tell me the mean and the variance, you'd say, get out of here. So I can't do it. You got to give me at least two. And we have a mechanism right now, and Ben says, well, give it some traction. The problem with that is your answer is going to be hypersensitive to whatever traction you build in through the prior. So I don't think that's a good answer, but it will give you a probability model. But I don't know if I would do it in practice, because I would be swaying everything by the prior a lot.
And so in practice, use more data points.
That's what I would really do. Thank you so much, Ben, for concluding on that. I would say go get more data. Get me at least enough information from data so I can say something about data. So if you're using improper priors throughout everything, and you find out that your posterior is improper, you don't have enough data built into the system to give you an answer. So we could change the prior, but I don't like it on a practical level because I'd be supplying an answer. It'd probably be leaning towards wherever I hyperparameterize everything. So more data. Let's come back next time, carry through this analysis again, and use more data and see what happens. So see you guys on Monday. Enjoy the weekend.